Hello and welcome to Chapter 2, Scientific Methods in Psychology. Slide 2. For many of you, I know the idea of science, math, and statistics may be scary or daunting. I want to reassure you all just how bad it ain't by making this as relatable as possible. First, I'll assert and defend the claim that psychology is indeed a science. But that'll only take a little bit of time. I do have a full-time job, so someone must think it's true. For the bulk of this lecture, we'll review the super fantastic way to answer almost any question about the natural world, including human behavior and experience, otherwise known as the scientific method. Slide 3. Do you even science, bro? Is psychology even a science? Well, we are claiming to use scientific methodologies, but even so, some claim it would never be a legitimate science. How could you possibly predict someone's behavior? It's not like a block on an inclined plane or adding chemicals together or anything. Well, in the words of Bart Simpson, eat my shorts. Au contraire, mon frère. While it's true that we cannot predict the behavior of any individual other than in a probabilistic sense, psychology is the most sophisticated of the sciences because we do have to deal with human variability. As a result, psychology has developed statistical methods for dealing with this variability. But let's start from scratch. What is a science? The word science derives from the Latin words scire or scientia, roughly meaning knowledge, and is currently used to denote an organized collection of facts that explains relationships between variables. The process by which facts are collected, analyzed, and interpreted is called the scientific method, which is used by psychologists to look at human behavior and experience. Why? Well, obviously because it is super fantastic. Further, we'll see through psychology that science is a process that doesn't lead to a final destination of capital T truth, but rather leads to models that explain natural phenomenon with more and more accuracy as new data refines the model. Slide 4. Before we get deeper into the super fantastic way to answer almost any question and how it's used in psychology, let's be honest about how psychology does in fact differ from other scientific fields. For starters, let's look at its history. Other sciences began gradually from the work of amateurs. Psychology, in contrast, began in Leipzig, Germany in 1879 by Wilhelm Wundt as a deliberate attempt to start a new science by people who are artificially scientifically trained in related or medical fields. These researchers were applying the methods of the natural sciences to questions of philosophy of the mind. Another thing that makes psychology different from other fields of science is the ethical concerns. Since psychologists deal with other humans and sometimes non-human animals, there are many protections in place and therefore rules that need to be followed to ensure the safety, health, and protection of research subjects. I'll have more to say about these ethical concerns at the end of the lecture, but know that for other sciences like physics or geology, they don't have these concerns, so this makes psychology and the other fields of science that deal with humans as subjects, this makes us a little different from those hard sciences of physics and geology. Slide 5. Okay, like I said, that was going to be short, so now that we are all on board with the fact that psychology is in fact a science, we can start looking at this super fantastic method known as the scientific method. Slide 6. Pretend you're goat herders. I know, it's super easy to do because everyone has real experience with herding goats. In herding your goats, you notice that they become unusually energetic, practically dancing in the afternoon when the goats are usually tired. You also observe that many of your goats snack on the berries from a particular bush in the late mornings. Well, after reliably observing this behavior, you form an educated guess or predictive statement, a hypothesis, that goats will become more energetic after eating from this bush. This leads to a general statement with better explanatory power, a theory, that there's something about the berries on that bush that are related to my dancing goats in the afternoon. Slide 7. This use of specific instances to lead to a general understanding is called inductive reasoning, and it's an essential part of the scientific process. Let's imagine that you are this goat herder and you're traveling a bit after having seen this phenomenon of dancing goats from eating berries, and then you come across a similar looking bush. Well, from your theory about that previous bush with the dancing berries, you could generate a predictive hypothesis that eating berries from this similar looking bush will also cause dancing goats. This use of a general understanding to predict the outcome of specific instances is called deductive reasoning, and it's just as important as inductive reasoning in the scientific method. If you do observe energized, dancing goats after they've eaten from this new similar looking bush, you can now tweak your theory to broaden its scope from one bush to a family of similar looking bushes. Thus begins the cycle of hypothesis leading to theories, which generate more hypotheses that stimulate research, whose results support or refine the theory, which generates more hypotheses that stimulates more research, blah, 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 blah. You get it. The goat example is a super loose interpretation of the discovery of coffee, by the way. I would personally like to thank those goats for their contribution to my morning ritual. Let's take a look at each of these steps of research in more detail. Slide 8. When asking questions about the natural world, we need to be both careful and specific about how we ask the questions because not all hypotheses are equal. If I were to say music does not evoke emotions, I might get a variety of reactions depending on how different people define those terms. To avoid this confusion, researchers use operational definitions for the language used in a hypothesis or research question. An operational definition is a definition that specifies the operations or procedures used to produce or measure something, ordinarily a way to give it a numerical value. Slide 9. So if I were to operationally define music to strictly mean instrumental music, the interpretation of the sentence already changes a little bit. If I further operationally define evoke as meaning stimulating facial expressions, I'm further narrowing the interpretation of the statement. Finally, if I take the term emotion to mean the garden variety emotions of happiness, sadness, disgust, or anger, as measured by changes in facial expressions, I've taken a simple sounding and somewhat controversial sentence and have qualified it or operationalized it to the point where it could be studied in a meaningful way. The devil is indeed in the details. The lesson to take home from operational definitions is this. When you see a claim made, make sure that you understand how the terms are being used before you determine its validity. But let's not get ahead of ourselves. We'll be talking about validity in just a little bit. Within this framework of clear language, a scientific hypothesis is generated. That is, you can test this kind of hypothesis because of how you've operationalized the terms. Slide 10. Whether a hypothesis is used to inductively reason up to a theory or is used to suss out the details of a theory through deductive reasoning, it can be defined as a proposed explanation that acts as a starting point for further investigation. And get this, if you craft a sentence that is the exact opposite of your hypothesis, it would be called the null hypothesis. And as confusing as this may seem, the goal of research is to reject the null hypothesis. That's right. Contrary to popular belief, scientific research doesn't prove anything. It either does or does not support a hypothesis, and the criteria for supporting a hypothesis is to have rejected the null hypothesis. All right, let's try to put some meat on these bones. So let's use that music example. Music does not evoke emotions. The null hypothesis of that would be, it is not the case that music does not evoke emotions. And the goal of research would be to reject this null hypothesis by providing evidence for its statistical improbability. I understand this is confusing with all the double negatives, so I won't dwell on it further, but it's a distinction that makes a difference, and it's a point worth memorizing. The goal of scientific research is to reject the null hypothesis. Slide 11. Through the process outlined earlier, where hypotheses generate theories that generate different hypotheses, that tweak the theories, that change the hypotheses, etc., scientific theories slowly become refined over time. It's a process of self-correction in the face of new evidence that prunes unnecessary parts of a theory while keeping the thriving parts, thus resulting in a theory that has maximal explanatory power, which is just a fancy way of saying it explains a majority of a particular phenomenon. Explanatory power is the superpower of a theory. To be clear, a scientific theory is more than just a guess, even though the terms theory and hypothesis are used interchangeably in regular conversation. For the purposes of this class, a theory will be defined as an explanation or model that fits many observations and makes accurate predictions. Just as not all hypotheses are equal, not all theories are equal. For a scientific hypothesis to be useful, it needs operational definitions to make it worthy of research. So, what makes a good theory? A good theory starts with as few assumptions as possible and leads to many correct predictions. In that way, it reduces the amount of information we need to remember. Beyond that, we'll go over 3 specific criteria for a good theory. First, falsifiability, or showing what evidence could count against a theory. 2, burden of proof, the obligation to show evidence to support a claim. And 3, parsimony, which is just another way of saying, all things being equal, we prefer simpler explanations. Slide 12. The philosopher Karl Popper emphasized scientists' willingness to disconfirm their theories by saying that the purpose of research is to find which theories are incorrect, which is kind of the opposite of how most people think of things. That is, the point of research is to falsify the incorrect theories, and a good theory is one that withstands all attempts to falsify. A well-formed theory is falsifiable. That is, it is stated in such clear, precise terms that we can see what evidence would count against it, if, of course, such evidence existed. Falsifiable does not mean we actually have evidence against a theory. If we did, it would be falsified. Falsifiable means we can imagine something that would count as evidence against the theory. A theory that makes no definite prediction is not falsifiable. For example, many physicists believe that ours is just one among a huge number, perhaps an infinite number, of other universes. Can you imagine any evidence against that view? If not, it doesn't qualify as a good theory. Slide 13. Burden of proof is the obligation to present evidence to support one's claim. In science, the burden of proof is on anyone who makes a claim that should be demonstrable if it is true. For a claim such as, UFOs from outer space have visited Earth, or some people have psychic powers to perceive things without any sensory information, the burden of proof is on anyone who supports these statements. If they're true, someone should be able to show clear evidence. Slide 14. When given a choice among explanations that seem to fit the facts, we prefer the one whose assumptions are fewer, simpler, or more consistent with other well-established theories. This is known as the principle of parsimony, and the story of Clever Hans, which is in your textbook, is an example of using parsimony to reach a simple explanation to a novel event. The principle of parsimony tells us to adhere to what we already believe, to resist radically new hypotheses. You might protest. Shouldn't we remain open-minded to new possibilities? Yes, if open-mindedness means a willingness to consider proper evidence, but not if it means the assumption that anything has as much a chance of being true as anything else. We do need to keep an open mind, just not so open that our brains fall out. If you want to know more about the Clever Hans story, I recommend that you check it out in the textbook. Slide 15. So, a parsimonious theory that can be falsified, but is currently unfalsified, and has met the burden of proof by presenting valid evidence for claims, has strong reasons to be trusted as a theory with explanatory power. Okay, this is a good start. Starting good. With this basic and bookish understanding of theories and hypotheses, we can start talking about studying them through research. So let's begin with the main subjects of psychological research: human beings. Slide 16. A population is the broadest group of people you are targeting. But since we can't test everyone in a given population, we have to settle for a sample, or a small group of people meant to represent your target population. This assumes that your sample is representative of the target population, a problem worthy of its own class. But general problems with sampling aside, let's look at how to resolve them through sampling methods. Slide 17. Researchers who expect the results to be about the same for almost everyone can use a convenience sample, a group chosen because of its ease of study. I can personally attest to how this form of sampling provides the fastest way to recruit for a study, because it's a first-come, first-served type of sampling that allows for quick and hence convenient, hint, hint, convenient sampling, recruitment of participants. What's the downside? It lacks the integrity of a random or representative sampling. Well, what if you don't expect the results to be about the same for everyone? Fear not, you have choices. They're just not as convenient. The more restrictions on your sample, the more intensive the recruiting process will be. For instance, a representative sample is one that resembles the target population in proportion of ethnic group, age, or whatever characteristics seem likely to affect the results. To get a representative sample of a target population, an investigator first determines what proportion of the residents belong in each category of interest. Then, they recruit participants to match those proportions. Of course, a sample that is representative in one way might not be representative in others. Moving on to a random sample. Random sample is one in which every individual in the target population has an equal chance of being selected. A random sample has this advantage: the larger a random sample, the smaller the probability that its results differ substantially from the whole population. However, while a random sample is theoretically the best, it is quite difficult to achieve. And lastly, we can look at cross-cultural samples. These are samples that contain groups of people from at least two cultures. Cross-cultural sampling is difficult because of the expenses, of the language barriers, and sometimes reluctance of people in some cultures to participate in unfamiliar tasks. Slide 18. Assuming, based on our observations, that we have chosen our hypothesis, our target population, and method of sampling, we need to next determine what kind of data we're collecting and what instrument we'll use to collect it. That is, how are we going to collect the data? Slide 19. This is where we review different research methods, both non-experimental and experimental. Slide 20. As we'll see, an experiment is a very specific thing with very stringent criteria. So let's start with something looser. Let's start with some non-experimental ways of getting information. These techniques are mostly considered qualitative methods because researchers collect data like written accounts of observed behaviors, as in naturalistic observations, or analysis of personal journals of a client, as in a case study might. In other words, it's not numerical data like that collected by quantitative methods. Slide 21. For biologists like Jane Goodall, who spent years observing chimpanzees in the wild, recording their food habits, social interactions, gestures, and way of life, there may not be a need to calculate the quantity of any event during her naturalistic observations, because it is the quality of the habits, gestures, and interactions that are of value. What foods were eaten? How did they harvest it? Do they recruit the help of others? Etc., etc. When your naturalistic observations revolve around a single individual, generally someone with unusual characteristics, you're engaged in what's called a case study or case history, which makes up most, if not all, of the work Freud used for his psychoanalytic theories, and it does still continue to be a valid method for clinical cases as a starting point for broader research questions about an unusual characteristic. Slide 22. Unfortunately, statistical analyses can't be done if numerical data isn't generated. Also, even if numerical data was collected, the best that could be done is a correlation, and this does not infer causality. And finally, non-experimental and qualitative methods are more prone to inconsistencies than experimental and quantitative methods because of the unreliability of researchers due to subjectivity and unconscious biases. Slide 23. One way to avoid these problems is to collect data on an instrument that is both reliable and valid. That brings us into the territory of research methods that are not qualitative but quantitative. That is, they collect numerical data to be used for statistical analysis. Slide 24. When using an instrument to collect data, there are many factors to consider: relevancy, reliability, and validity. By the way, when I say instrument, you can either think of a physical instrument like a brain scanning machine or a heart rate monitor, or you can think of something like a survey or rating scale that gets filled out. These are all data collecting instruments. Whatever the end result of the instrument, are they predicted in a straightforward way by the hypothesis? For example, why would you collect someone's heart rate unless you expected it to change in a meaningful way? Your instrument should collect data relevant to your hypothesis. It should also be reliable. If two different researchers are observing the same behavior and using the same scale to classify or rate the behavior, is the same behavior classified or scored the same way by both researchers? Questions like this address the inter-rater reliability, and of course you want the answer to be yes. You want your instrument to behave consistently regardless of who is using it. Speaking of which, if it's a questionnaire that scores a personality trait or intelligence, do individuals who score higher on the questionnaire at one point in time also score higher at other points in time? That is, does the score remain consistent for the same person if they are retested at different days and times? This kind of reliability is called test-retest reliability. Assuming we have an instrument that is relevant and reliable, we need to address its validity. Can effects within the experiment be attributed to the variables that the researcher intentionally manipulated? Is your manipulation making a difference on the endpoint your instrument is collecting? Or is something else driving the change you're seeing? These are concerns about internal validity. Finally, how widely can the findings be generalized? Do they apply to different populations in different places at different times? These questions address concerns about external validity. Slide 25. Once we have an instrument that meets our criteria of relevancy, reliability, and validity, we can begin collecting data, which leads us to our last non-experimental method, the survey. Slide 26. A survey is a study of the prevalence of certain beliefs, attitudes, or behaviors based on people's responses to specific questions. That is, it's a report of people's answers on a questionnaire and is easy to conduct, but, unfortunately, also easy to deceive. Survey results are affected by a few things. First, sampling. Getting a random or representative sample is especially important with surveys. 2, seriousness, with the assumption that those who take it more seriously will provide more genuine and trustworthy answers. And then finally, the wording of survey questions. The wording is important because we could fall into surveyor bias, which happens when the wording of the survey questions encourage answers the surveyors hope to receive, rather than being an honest reflection of the thoughts provided by the participant. Let's take a look at the difference between these survey questions. If you were to be asked, how dumb is fill-in-the-blank politician when it comes to foreign policy, that sounds a little bit different than, please describe your politician's position on foreign policy. Or how about this? The difference between, where do you like to party, as compared to, what do you like to do on weekend evenings? How about this? How happy or unhappy are you with the rate of current school board funding and the Common Core curriculum? That's confusing. It's actually 2 questions in one. So that would be different if it was laid out as, How happy or unhappy are you with the rate of the current school board funding? Separate question, what do you think of Common Core? And then finally, think of the difference between these questions. Do you always shower before bed? Versus, how many nights a week do you shower before bed? Regardless of which of the form of a question you like, you can admit that the answer to the different forms of questions will be different. And that difference is what I'm talking about when we talk about surveyor bias. And surveyor bias is important because it demonstrates that the wording used on surveys can affect the results that you receive from them. Slide 27. Well, how do you analyze the data you've collected from a survey or other non-experimental method once you've collected it? Well, you would use a correlational analysis. Slide 28. A correlational analysis tells you whether two variables are related and the strength of that correlation. To measure the strength of a correlation, researchers use a correlation coefficient, which is a mathematical estimate of the relationship between two variables. It works like this. A correlation coefficient of 0 indicates no consistent relationship between two variables. A coefficient of +1 or -1 indicates perfect relationship. That is, if you know the value of one variable, you can predict the other with perfect accuracy. In psychology, you probably will never see a perfect +1 or -1 correlation coefficient. The positive correlation, the +1, or anything between 0 and +1, means that one variable increases as the other one reliably increases. A negative coefficient, such as the -1 or any score between 0 and -1, means that as one variable increases, the other reliably decreases. And a 0 correlation indicates that as one variable goes up, the other does not consistently go up or down. A correlation near 0 can mean that two variables really are unrelated or that one or both of them were poorly measured. Slide 29. Figure 2.9 shows scatter plots for 3 correlations. This is real data. Each dot represents one student in an intro class. The value for that student along the y-axis represents percentage correct on the final exam. On the first graph, the values along the x-axis represent scores on the first test in the course. Here, the correlation is a plus 0.72. indicating a fairly strong relationship. Most of the students who do well on the first test also did well on the final, and most who did poorly on the first test also did poorly on the final. On the second graph, the x-axis represents times absent out of 38 class meetings. Here you see a correlation of negative 0.44. This negative correlation indicates that, in general, those with more absences had lower exam scores. The third graph shows how the final exam scores relate to the last 3 digits of each student's Social Security number. As you would expect, this correlation is close to 0. Slide 30. Unfortunately, just because we know that two variables A and B are related does not mean we know which variable is affecting the other. That is, we don't know the direction of causality. It could be that A causes B or B causes A. This is called the directionality problem. The change we're seeing could also be caused by some third variable, C. This brings up the third variable problem. For example, how much sunscreen people use is positively correlated with their chances of getting skin cancer. Does that mean that sunscreen causes cancer? It's more likely that people who are at risk for skin cancer because they spend too much time in the sun are the ones who are wearing more sunscreen. So there's an example of a third variable that interferes with the first and second variables. Here's another fun correlation. The number one predictor of motorcycle accidents is tattoos. Do we conclude that tattoos cause accidents? That riding a motorcycle causes tattoos? No. Maybe there's a third factor, and there is, like risk-seeking behavior. Risk-seeking behavior accounts for both getting tattoos and riding a motorcycle, and maybe behaving less than safe while on a motorcycle with said tattoos could be the reason why the number one predictor of motorcycle accidents is tattoos. Just saying. A final problem with correlations is that sometimes people think they see one that doesn't really exist. That is, people see what they expect to see. When people expect to see a correlation between two events, for example, like sugar and activity levels, they remember the cases that support the connection and disregard the exceptions, thus perceiving an illusory correlation, an apparent relationship based on casual observations or unrelated or weakly related events. And it is for these reasons that researchers have the maxim, correlation does not equal causation. But, limitations aside, correlational analyses are very useful for populations and questions that are difficult or unethical to pursue in the laboratory, like looking at the detrimental effects of cigarette smoking or the effects of alcohol abuse during pregnancy. We do not live in a world with research studies that ask people to smoke cigarettes or drink alcohol while they're pregnant just to see what the difference is between people who don't smoke or don't drink during pregnancies. Instead, we can use correlations to demonstrate a link from occurrences in real life. Slide 31. And here's just a bunch of fun correlations just to drive home the point that correlation does not mean causation, right? So the first graph here shows that there is a correlation between divorce rate in Maine and per capita consumption of margarine, two things that should have nothing to do with each other, yet are correlated. Another one in the middle is the age of Miss America and the murders by steam, hot vapors, and hot objects. Not just death by them, murder by them. And then finally, this is my favorite, per capita consumption of mozzarella being correlated with civil engineering doctorates, right? So if we want more civil engineer doctorates awarded, we all know what to do. Eat more mozzarella. I like that theory. I'm sticking to it. Slide 32. We did it. We have arrived at the gold standard method to use for our super fantastic way to answer any question about the natural world, including human behavior and experience. Experimentation. Slide 33. Experimentation is the one method we have at our disposal to show causation. When experimentation hears that correlation doesn't equal causation, it steps forward confidently and says, "Hold my beer, I got this." Because being able to demonstrate causation is the very superpower of experimentation. In fact, it's the most powerful claim that can be demonstrated in a scientific method. In an experiment, an investigator manipulates an independent variable to determine its effect on the dependent variable. What? Let's revisit the dancing berries from the beginning of the lecture, or at least the active ingredient, caffeine, to make more sense out of these independent and dependent variables. Slide 34. In general, experimenters manipulate something, let's say caffeine amount, to see how that changes something else, let's say talking speed. In this instance, the caffeine is the independent variable, and the talking speed, since its change depends on the caffeine, get it? It depends on it, dependent variable. It is the dependent variable. This assumes you're working with a hypothesis like caffeine increases talking speed. Slide 35. In order to test the effects of an independent variable on a dependent variable, you need to break your sample up into groups. The experimental group gets the independent variable, caffeine, and the control group does not. The out-of-control group gets way too much caffeine. Get it? Dad joke. The dependent variable is measured in all groups. If we did this with the caffeine example, we would expect talking speed of the experimental group to be measurably faster than the control group. A key procedure for any experiment is to ensure the participants have an equal chance of being assigned to a group. The importance of random assignment is to safeguard against any group having a disproportionate amount of people with any particular trait. For example, you could pull numbers out of a hat or use an online random number generator to spit out a random sequence between 1 and 100. Then you could divvy up the numbers into groups by using the first and second halves to determine which participant goes into which group, or you can use every other number of this random string of sequences, and every other number, the odd-numbered people would go into one group and the even-numbered people would go into the other, regardless of the method. By randomizing, you're ensuring that, on average, you will not be getting a disproportionate number of traits in any one group. Slide 36. Once you have randomly assigned groups, you need to control for variance or any changes in the way the study is administered to each participant. This goes from the room that they are tested in to whether or not they've eaten or drank anything before testing. When controlling for variables in a study, we're looking to reduce confounding variables, or variables that could influence the outcome you're looking at, independent of your manipulation. For instance, you may want to control for any caffeine ingested before a caffeine study, considering its effects can last up to 5 hours. Otherwise, subjects might show up for testing already caffeinated from a coffee or soda. Or you might want to consider the timing of your testing if your sample is college students, if you think that exam stress could affect the results. Either of these confounds could render your control group useless or have an effect on talking speed that prevents you from making a causal statement about caffeine. Also, for the experimental group, these confounds may artificially boost the effects of the caffeine. Confounding variables are things a researcher knows or thinks may confound their results if they don't control for them. Unfortunately, the more control you exert in the lab, the less you can generalize in the real world, so you need to strike a balance. Slide 37. Even after controlling for confounding variables, experiments are prone to the effects of demand characteristics, or cues that tell participants what the experimenter expects of them, and also experimenter bias or expectations. To minimize demand characteristics, experimenters often try to conceal the purpose of the experiment. Further, an experimenter's expectations influence the interpretations of behavior and the recording of data. To counteract this, researchers use the firewall of blinding in studies. In addition to leaving participants blind to what is expected, to ensure objectivities, investigators can use blind observers who do not know what results are expected. Slide 38. This plays out in either a single or double-blind study design. In a single-blind study, either the researcher or the participants, usually the participants, are unaware of the expected results. Think of any taste test where participants are asked to choose one of two things that they've tasted. While the researcher knows what each sample is, the participant is blind to it and must make a choice based merely on sensation and perception, not expectations. In a double-blind study, neither the observer nor the participant know the researcher's predictions. For instance, we may have a study where I know which group each participant is in, but I don't tell my technician who's administering the test so that they don't give away unconscious nonverbal cues that the participant could pick up on to influence behavior. Slide 39. Let's assume you've done everything right. You have, based on observations, made a hypothesis that you've crafted with operational definitions for a theory that is parsimonious, falsifiable, and takes on the burden of proof. You've determined whether you're doing an observational or experimental study design. If you're collecting quantitative data, you have an instrument that is relevant, reliable, and valid. You've selected your population, determined your sampling methods, and have randomly assigned your participants into your experimental and control groups. You've controlled the confounding variables and dealt with experimenter bias and demand characteristics through blinding. Now you've collected all of this data. What do you do with it? That is, how are we analyzing the data that we've collected? One word: statistics. Slide 40. The first level of analysis is to provide descriptive statistics, named as such because they describe your observed results in the form of mathematical summaries. Slide 41. When summarizing the results of an experiment, we care about the central score, that is, the middle or average. And there are three ways to represent an average, or what is also known as central tendency. One way of presenting the central score of a distribution is via the mean, determined by adding all the scores and dividing by the number of scores. This is what is commonly meant when we say average. If I were to calculate the average age of the students in my class, or the average scores on a continuous scale, I'd be using the mean. The mean is especially useful if the scores approximate the normal distribution, or normal curve, which is a symmetrical frequency of scores clustered around the mean. Another average is the median, the middle score after all the scores have been arranged from highest to lowest. An appropriate use of a median is when you hear about differences in salaries. Because most of the world's wealth is clustered to a slim minority of individuals, wealth distribution does not fit on a normal bell curve. Hence, median is a more appropriate measure of central tendency. Median can also be used when collecting data where responses fall into categories. For instance, if you're asking participants to rate something as either smelling like root beer or peppermint, and 20 participants choose root beer and 30 choose peppermint, you can't report a mean of 1.6 because there is no category between 1 and 2. Category 1 is root beer, category 2 is peppermint. There is no root mint category or pepper beer category. This kind of category data is called nominal data. In addition to using the median, you can also use the mode on this kind of data. The mode is the score that occurs most frequently. Once we've reported the descriptive statistics of the data we've collected, we may want to make inferences about any differences seen between our groups and whether they can be generalized to a larger population. Enter inferential statistics. Slide 42. Inferential statistics determine the probability that purely chance variation would achieve a difference as large as the one observed. That is, it determines how confident you can be in your results by comparing your observed results to what you would expect to happen by random chance. So if you're using inferential stats to calculate the probability that a given research result would have arisen by chance, you would want that probability to be low, very low. Walk through this with me. If you have a result that you want to impress somebody with and they ask, yeah, but what's the probability this is just due to chance? You want to be able to say with confidence, the probability of this being due to chance is low. It's quite low. That probability of this result being due to random variation, that probability, it's a low probability, son, okay? I don't know why I just got indignant at the end right there. It's flashbacks from giving too many poster presentations. Anyway, I think you get the point. Slide 43. The results of inferential statistics is summarized by a p-value, p as in probability. The smaller the p-value, the lower the probability, and the more impressive your results. The usual agreement is that if p is less than 0.05, researchers consider the results to be statistically significant, which chance alone would be unlikely to produce. The p-value of 0.05 represents either a 5% probability the results are due to chance, or a 95% confidence that your results are not due to chance. Other, more stringent criteria for statistical significance include a p-value of 0.01, and this would represent a 1% possibility that the results are due to chance, a p-value of 0.001, representing a 0.1 probability that results are due to chance, or a 99.9% confidence in your results. Impressive indeed. There are three factors that can influence statistical significance, though. There's the size of the difference between the groups. The larger the difference, the better. There's the number of research participants in each group. Again, the more the better. And finally, there's the amount of variation among individuals within each group. And this variation you would want to be kept small. So, the larger the difference between the groups, the larger the number of people in each group, and the smaller the variation of the individuals within each group, the better. Slide 44. Critiques and objections to the procedure yielding a p-value exist and have been growing. One objection is that it falsely implies an all-or-nothing judgment. Either something is significant or it is not. More realistically, results range along a continuum from convincing to unimpressive. A second objection is that we should care about the size of the effect, not just whether or not it occurred. Given a large enough sample, it would be possible to get a low p-value even for a tiny effect with no practical importance. To address these critiques, some researchers are suggesting the raw p-value be reported regardless of whether it meets an arbitrary criterion like 0.05 or 0.01 or 0.001. This lets the readers determine significance for themselves. Currently, the trend is to present the means and the 95% confidence intervals for each group. Presenting data with confidence intervals enables readers to judge for themselves how large and impressive the difference is between groups. Slide 45. We did it, gang. We've covered basic research methods used in psychology. And even though I placed a value on certain methods than others, psychology is not limited to one technique or research method. Experiments are good for causality, but they're artificial because of all the things that you need to control for. Correlational studies, on the other hand, allow for more realistic environments, but unfortunately can't infer causality. Naturalistic observation is the most realistic, but the least powerful for inferring causality. So, using a combination of these three is not unheard of. Just because there are distinctions between experimental and non-experimental methods doesn't mean that you need to stick to just one. You can mix and match so long as you have integrity in answering the question that you've asked. Slide 46. Most scientific researchers are scrupulously honest in stating their methods and results. A major reason is that anyone who reports a scientific study must include the methods in enough detail for other people to repeat the procedure and, we hope, get similar results. Replicable results are those that anyone can obtain, at least approximately, by following the same procedures. Scientists do make certain allowances for small effects. When researchers try to verify a small effect, they use a meta-analysis, which combines the results of many studies as if they were all one huge study. A meta-analysis also determines which variation in procedure increase or decrease the effects. However, if no one can find conditions under which the phenomenon occurs fairly consistently, we do not take it seriously. This rule may seem harsh, but it is our best defense against error. Psychological researchers have been increasingly concerned about the replicability of their findings. Slide 47. And here is a hierarchy of evidence, starting at the bottom with anecdotal reports, moving up the pyramid through observational, qualitative type studies, up to random controlled trials, experimental studies, and then at the very top live the meta-analysis. Take-home point: meta-analysis rule the world. Slide 48. All right, let's wrap this up by just talking about some ethical concerns with the way that psychologists treat their subjects, humans. Slide 49. Once you've developed your research study, but before you begin recruiting, you need the approval of an institutional review board, or IRB, whose responsibility is to ensure the protection of research subjects. For human participants, the IRB judges whether the proposed studies include procedures for informed consent and whether they safeguard each participant's confidentiality. An IRB also tries to prevent risky procedures. A committee would also ban procedures that they consider seriously embarrassing or degrading. Before conducting any study on people, researchers ask for their informed consent, a statement that they have been told what to expect and that they agree to continue. When researchers ask for volunteers, they describe what will happen. Participants are told that they have the right to quit if they find the procedure too disagreeable. Special problems arise in research with children, people with mental retardation, or others who might not understand the instructions well enough to provide informed consent. In such cases, researchers either consult the person's guardian or nearest relative to receive assent instead of consent. Slide 50. And sometimes psychological research involves non-human animals. Animal research has long been essential for preliminary testing of most new drugs, surgical procedures, and methods of relieving pain, and most psychologists support some kind of animal research, but draw a line somewhere separating acceptable from unacceptable research. Professional organizations such as the Society for Neuroscience and the American Psychological Association publish guidelines for the proper use of animals in research. Further, colleges and other research institutions maintain laboratory animal care committees to ensure that laboratory animals are treated humanely, that their pain and discomfort are kept to a minimum, and that experimenters consider alternatives before imposing potentially painful procedures. Slide 51. Congratulations, everybody. We did it. We made it through what I consider the most difficult chapter of the whole semester. Give yourself a round of applause. See you next chapter.